Tell your neighbor the answer to this question.
No, I swear. I mean, I don't really care, but it's more just like people don't think I'm so dumb. Just like she talks about it, you know, she was like, there's an experience that I'm asking back. So she was trying back.
Correct answer is. Okay, folks, just quick little heads up of this chapter. This lesson has the most far-reaching implications in terms of the concepts and what we're using. Like, this is like the most important foundational lesson. Just throwing it out there. No pressure. Kind of an encouragement to focus. What do you say? Correct answer is the slower this goes, the greater this is. B. Good with that?
I feel like that's not right. How do you calculate?
Have a conversation with your cohorts around you.
Oh, no, it was, he had a chart on the video. Yeah. I can remember it.
I didn't have it together. I had one.
Yeah. Boom.
Correct answer is
A.
the fastest light can go is the speed of light in a vacuum. C. C over C. 1. A. Good with that? All right. Proof of concept. No.
Oh my god.
Okay. I'll do this twice. Once for this side and then second time for that side. Okay. So here, actually I'll do it 3 times. Once for the video. Okay, see the bend?
That's so cool.
Yeah, it is. It is cool. All right. So do you see how it's bending when it goes from air into water? So how it's not straight. For you all? Okay, do you see it? Can you see it over here? Good with that? Okay. So when Light goes from one medium into the next when it changes materials. It causes a change in speed, and therefore it causes a change in direction. Okay, so you good with that? Show me with your arm where the normal line is for this example. Where's the normal line for this interaction? Perpendicular to the surface, right here. Good with that? Okay. So when I was in your shoes and they told me, hey, light bends because it changes speed, that didn't really sit well with me because I'm like, okay, in my car, if I ever hit the brakes, it's not like I'm like, turn, or like hit the gas, like, turn, like, why does changing speed mean a change in direction? Does that make sense? Okay. So here's my attempt to explain why that happens. Okay, so light is a wave, electromagnetic wave. Think of a drone shot of a beach. The waves crashing. You see from like really high up. Usually the waves don't crash all at once. Usually it's like a line, like kind of like a domino. You know what I'm talking about? Okay. So the waves don't change mediums all at the same time. Here's the analogy. Let's pretend you're in a wheelchair and you're rolling along the sidewalk and one of your wheels goes off of the sidewalk into the grass. What happens to the speed of that wheel that's now in the grass? Slows down. What happens to the wheelchair as a consequence of that one wheel slowing down first? It turns until both wheels are now in the grass, going slower. But now you're facing a different direction. You're traveling in a different direction. Does that make sense? So the parts of the wave transfer to different materials at different times, which causes a change in direction. You okay with that? Okay. Okay, this is off of your reading quiz. Sorry, should have warned you. Whew, that's bright.
When it's going to reflection, slow material, but access from a lower end to a higher end, it's straight weight, then it's in the opposite. So it goes from a higher to a lower.
What do you guys say? Okay. When it goes from a slower to a faster, that means the N1 is greater, it's slow, to fast, has a lower index of refraction. Okay. When it goes from slow to fast, when it goes from high to low, it bends away from the normal line. A is correct. Good with that? As light goes from air, index refraction 1, to water, index refraction of 1.33. Okay. In your brain, momentarily. I'll turn you loose on conversing here momentarily. Thumbs up when you have a guess. Tell your neighbor. It's going from a high to a low speed. High is faster in air, slower in water. Correct answer is A. Okay. It's bending towards the normal line. B would be no refraction. Okay. Here's my wheelchair analogy. You're in your wheelchair. You're looking bird's eye view. You're going from the sidewalk to the grass. This wheel is going to go off the sidewalk first into the grass. It's going to slow down and cause it to bend which way? Towards the normal line. Good with that? Okay. All right, this next question, it's super easy, but your life will be ruined on this test if you don't get this right. I want don't say it out loud. I just want you to figure it out yourself. In this chapter, what do we always measure the angles from? Always from the normal line. Correct answer is A. Okay? Don't mess that up. It's just going to be a train wreck. Okay? Good to that. Always from the normal line. A. Tell your neighbor. Correct answer is C. Here's the wheelchair analogy. You're going from the grass, slow, to the sidewalk, faster. As you go off the grass, go from the grass onto the sidewalk, this wheel is going to speed up faster sooner. That makes sense? Okay. C is the correct answer. All right. So when you are to answer these questions conceptually, I'll show you how to answer these questions mathematically momentarily, but to answer these questions conceptually, there has to be one factoid that you have memorized. What that is completely up to you. Okay. Whether you remember, okay, when it goes from low to high index refraction, it bends towards the normal line. If you remember, if it goes from fast to slow, it bends towards the normal line. If you do the wheelchair thing, that's probably the least memorized because you can kind of figure it out. For me, here's what I've memorized. This demonstration. Okay, this is where I start from. I'm really visual. Like I've locked in this. This is in my brain. This is where I start from when I do refraction. Like if someone throws me a refraction problem, like okay, I gotta think about this. Okay, water. Okay, light goes from air into water. It's gonna look like this and bend towards the normal line. Okay, and then I build my case from there. You got to have something to start with. Okay, so so let me describe in detail what's going on here. So at every interaction, every boundary, there will be one part that's refracted and one part that's reflected. Okay, you can see the reflected part here. That's not really what I'm talking about, but this obeys the law of reflection. And then the other part is refracted, and it goes in. You see how it bends towards the normal line. Okay. Now, if I go from water into air, okay, so a lot going on there. It's like a laser show. Here's what I care about. I'm going from water into air. Okay, bends away from the normal line. Here, this is reflecting off the glass. Here you can see some of it's getting out to here, but some of it's being reflected back into the water. Good with that? Okay. Okay, for you all over here. Okay, going in. Okay, from air to water, bends towards the normal line, and then from water to air. Yep. Water to air, it bends away from the normal line. Good with that? All right. Okay. I'm going to turn on the lights here. 3, 2, 1. Oh, well, whatever. Okay. So, example. They were going from water into glass. Bless you. Okay. Show me with your arm the normal line in this example. Show me with your arm the normal line. Some of you are getting it. It's always perpendicular to the surface. Normal line looks like this. Okay. As it goes from water into glass, it goes from a low index of refraction to a high index of refraction. It goes from fast to slow. So what do we anticipate this is going to do? Tell your neighbor, bend away towards the normal line. As it goes from water into glass, it goes from a low index of refraction to a high index of refraction. It goes from fast to slow. It's going to bend towards. So this would be no refraction. Does that make sense? It's going to bend towards it. Does that make sense? Here's the normal line. It's going to bend towards it. Okay. Wheelchair analogy. As we're going from the sidewalk into grass. Okay. Conceptually, you gotta start with something. Okay. Something needs to be memorized. Okay. So our theta 1 is going to be here. Theta 2 is going to be here. Angle of incidence, angle of refraction. Okay. To calculate this, we're going to use Snell's law. I kind of like the German pronunciation or German version. Schnell. Just more fun to say. Okay. 1 corresponds with what it starts in. 2 corresponds with what it ends up in. Okay. So you have 1.33 sine of 28 degrees. So make sure you are in degree mode. And 2 is 1.52 times sine of theta 2. This is what we're looking for. So this becomes 0.62. And that becomes 0.43 maybe. And theta becomes 24 degrees. I'm going off of memory, so I might have missed that.
You want to use any decimal points for the degrees?
You can if you want to. Point 0.41. 0.41. So we got 24 degrees. Does that match with what we thought was going to happen? Is theta 2 going to be more or less than 28? It better be less because we said it bent towards the normal line. So if you get something different, either you remembered something wrong or you did some wrong math. Good with that? So this would be the mathematical way to figure stuff out. If you're like, I don't remember concepts, this is, I guess, your safety net. You can make up a problem. Figure out what it's supposed to do. Good with that? So you could do the memorized approach, you could do the wheelchair approach conceptually, or you could do the math approach. Okay? Good with that? Questions there? Have a conversation. Correct answer. Okay. Let's start mathematically. What's theta 1? Is it 0 or 90? We always measure the angle from what? Normal line. What's the angle between the incident ray and the normal line? 0. So, pre-cal folk, what is the sine of 0? 0. Okay. Sine of 0 is 0. So this side's 0. This side has to be 0 too. Okay. Wheelchair analogy. You're going from the sidewalk straight on into the grass. Both wheels hit the grass at the same time. They're both going to slow down, but because they slow down at the same time, there's no change in direction. Okay? When you go headlong, perpendicular into the material, there is a change in speed, but there is no change in direction. Good with that? Thumbs up when you have a guess. Converse with your cohorts. Correct answer is? Correct answer is C. Okay. A bigger change in speed is going to constitute a bigger change in direction. Okay. Let's, from our wheelchair analogy, air's your sidewalk, water's grass, your glass is like mud, and your diamond's like sand. You ever tried to ride your bike through sand? Doesn't go very well. Okay. So you're going from super slow to fast. It's going to like cause a bigger change in direction. So the bigger the contrast of your indices of refraction, the greater the change in direction is going to be. Okay. Good with that? Okay. Here's what I want you to do. Everybody's going to grab a cup in the back. Don't do it yet. In the cup is a dot. You're going to pair up. One person is going to be the observer. They're going to take their cup with the dot and put it as far away from them as possible. And then they're going to stand back and be an observer, or they're going to stand back until the dot of the cup in the cup just disappears below the rim of the cup. Okay. Next person is going to fill their cup up with water, and they're going to pour in, like fill it up to like 80% full ish. Okay. And they're going to pour in the water in the cup until the observer is amazed. And then switch roles. Okay. Cups are in the back. Sink, water's in the sinks. You can do lab tables, desks, whatever.
I prefer not to use it.
There's the dot. Tilt it until just away, and then I'm going to pour water in. And all of a sudden, you see the dot. Okay. Go ahead and switch roles after you've made your observations. Sorry. I'll give you some.
I was able to do it myself just by leaning over, but keeping my feet in the same place.
Okay, once you have both people have done it, go ahead and dump your water back in your sink and have a seat.
It took me a couple minutes to realize where I was and like who I was, like to regain consciousness after that. I mean, it was like just crazy.
All right.
I just feel closer to God.
Remember that light, sorry, your eyes are the receiver, the catcher of light. They're not the things that emit light. So in order for you to see something, light has to be coming into your eyes. Okay? The dot is reflecting light off of it in all directions. Okay? You were not able to see the dot because the ray of light that would have reached your eye got intercepted, ran into the edge of the cup. Does that make sense? Could not see the dot. But then you filled the cup up with water. So when light goes from water into air, tell your neighbor, is it going to bend away or towards the normal line? Is it going to bend away or towards the normal line? Away from the normal line. So, this ray, instead of going straight through, here's our normal line. It's going to bend away from the normal line into your eyeball. And you can see it. Good with that? Now, here's the catch. When we see things in life, I see the marker sitting on the desk. I assume it's there because I see it's there. It's not like I go, oh, oh, shoot.
Imagine if you just did that. That'd be
Okay? We always assume light goes in a straight line path. We never really think about light bending. Okay? So we think the dot is right there as if light didn't bend, took a straight line path. This is the apparent depth. Where the object appears to be. Light we don't think about light bending. Okay? Does that make sense? Okay. So that's the apparent depth. So we assume, so when you're doing this, here's the ray that goes into your eye. Just make that a straight line. That's where you think you see it. Okay. So here's where the fish actually is. From your point of view, where does the fish appear to be? Where did the dot appear to be? The dot appeared to be here. The fish appeared to be here. Shallower than it really is. So the fish is actually here. That's where the physical fish is. To your point of view, it looks like it's here.
Oh, okay.
Oh, I thought we were talking about what this year.
Okay? So if you find yourself flying over the Canadian wilderness and your pilot has a heart attack and crashes, then you have to survive by spearing fish. You know what book I'm referencing? The Hatchet. I mean, that's a classic. Okay? He references science teacher. I'm like, yeah, he did. Where are you going to throw the spear? There we go, below the fish. Okay? So you see the fish, don't aim right at it. Aim down here, where the fish actually is, even though you see it here. Good with that? Now, funny thing, we always ask from our point of view, but no one ever asks, what does the fish see? Like, what is the fish's point of view? Have a conversation. That's some impressive mental telepathy going on. It's like, what do we think? Okay. So, the fish's eyeball is the recipient of the light. So, light is coming off of the spear. We're looking at the spear. And it bends from air to water, bends into the fish's eye towards the normal line. The fish appears, the spear appears to the fish in a straight line path up here. A, above to where it actually is. Good with that? Okay. That's all I got for today.